Okay, so partial differential equation. Partial differential equation is a differential equation similar to the one we discussed last semester and even this semester when we use Laplace. We solve it in analytical method. We solve it in Laplace. You are going to solve them later on, inshallah, level 3 using numerical method for first order, second order. In ordinary differential equation, we have y and we have x. X is the independent variable and y is the dependent, which is value depend on x. For partial differential equation, the situation is we have y, but we have more than independent variable. We have x, we have t, we have whatever we call them, these variables. So here we will differentiate with respect to the variable itself. I mean, we may have as example, my function is u, which is function of y and x. I may differentiate with respect to y only, or with respect to x only. For this, it's partial differentiated. For that, we call them partial differential equation, PDE, in front of ODE, ordinary differential equations. Many of the fundamentals and principles discussed last semester are applied here, such as linearity and linearity. You remember when we talk about linear or differential, what we said as example, when we have y dash equal to x plus 1, okay, it's linear. But when we have as example y dash plus y square equals 7, y square here is non-linear because square root, exponential, logarithmic, all these functions will produce a nonlinear equation. So things discussed previously in first order and second order differential equation last semester are applied here. Also homogeneity. You remember homogeneous and non-homogeneous. We just let me remind you. When we had second order differential equation, ordinary differential equation, as example, y double dash equal to x plus 2x minus 2y minus 1 as example equals 0. This is homogeneous. But if it is equal to exponential 2x, this is non-homogeneous. Now because we have function on the right hand side, it's not equal to 0 anymore. And these actually equations, homogeneous and are so applied in partial differential equation, have many applications. It's not new. It's not new. What happened, scientists found that, you remember the story for function, I talked about it many times, even last semester if you remember, when the scientists talking about Newton, Galileo, and these scientists was working on functions and the relationship between things. They found sometimes the function is related to one variable, but sometimes it's related to more than one variable. Example, talking about 18th century, the conduction of heat in a solid body. This is example. Heat and heat flow, something related to chemical engineering. Another example, space vehicle reentry problem, taking it to the orbit or removing it from the orbit. This is something related to control and to mechanical engineering. Transfer and dissipation of heat, which is related to mechanical and chemical, and even to civil, even to electrical also. So it's applied in many, let me say, physical systems and natural systems. For that, we need to know how we deal with partial differential equations. Example here, you see this example. You remember in partial differential equation, what we did was we write partial. Sorry, let me write it using paint, maybe paint. Okay, you remember y, okay, y dash equal, let me say 2x, okay. This mean y dash, it mean d y over
dx.
Excellent. So d, it means differentiation of y with differentiation of x. It means rate of change of y with respect to x. It means slope gradient. It means y2 minus y1 over x2 minus y change from one position to another position with respect to the change in x. So definitely we'll say, okay, let me say this is y, sorry. This is y. Okay, then it will be 2 only. Now, in partial differential equation, y will be function of two variables or more, such as 2x plus, as example, 4t. Okay, 4t. Now here, x and t are the independent variable. Y is the independent. When we want to differentiate y, we will not use d, this d. You remember d? But we will use this simple, partial. Okay, it's like d in italic, or let me say it's simple in Latin. Okay, y, it means partially derivative of y with respect to whom. Now we need to decide, are we going to differentiate with respect to x or with respect to t? Which one of them you need to specify? Such as example x. When I say differentiate with respect to x, it means t here, we don't touch it. It's constant, treated as a constant. Okay? We only differentiate x. So we will say, okay, this is t, 2 only. Why? Because we differentiate this part, it becomes 2 with respect to x. When we differentiate this part is a constant, it becomes 0. So for that, the simple we use here, as you can see, this simple is partial square u of xt. My function is u. The name of the function is u, which is the dependent variable. My independent variable is x and t. Now, partial here, x square, it means I differentiate the function u twice with respect to x. It means I differentiated with respect to x. The result, I'm going to differentiate again with respect to x. While this is equal to partial u over partial t. It means I differentiate the function with respect to t. By the way, when you partially differentiate u with respect to t, it means keeping x as a constant. Okay, by sometime we do this notation. This notation, rather than we write in the previous notation you see here, we write partial square u over partial x square, partial u over partial t. But here uxx, it means u has been differentiated partially with respect to x first and then second with respect to x. While here u partially differentiate with respect to t and then with respect to x. I mean, the result after we differentiate with respect to t, we come to partially differentiate with respect to x. With example, I will explain, but let me just go through the general ideas here. Linearity and nonlinearity. If I come here, I will say these PDE, partial differential equations, are linear. Let me see. 2 uxx means you differentiated twice with respect to x. Multiplied by 2 is a constant. I'm thinking with the question how I can measure if it is linear or non-linear. uxt is fine, no problem here. utt is fine also, no problem here. ux also fine, it's multiplied by constant 4, 3, 1, it's okay. Cosine tt, this is the independent variable, it's fine to have function of the independent variable. Okay, so there is nothing here to tell me that this is non-linear equation. This is linear. Let me go to the second equation. 2 uxx, it's fine. Minus 3 ut, it's fine. 4 ux, it's fine. Nothing here is non-linear. But when I come to this, 2 ux is fine, but uxt, it means my function u differentiated with respect to t first and then with respect to x second. But it rises to power 2. You remember 2? 2 is squared. It's non-linear. It's not like straight line. It's non-linear. It's parabola. We call it parabola. Now, this is sort of non-linearity in the equation. The same thing here. Uxx, it means you differentiate twice with respect to x, but there is square root. Square root also parabolic, but in the opposite, similar to parabolic. Parabolic is this way. I don't know if you see me or not. You can see me? You
Yes,
see?
doctor.
Yeah. This is the curve of parabola, which is x square. Square root is this side direction. Okay, this is u, like u is x square. In this situation, in this way, is square root 2. So let me back. More examples on linear and non-linear. This one is partial square u over partial t square equal exponential minus t. T, by the way, t here is independent variable. It's fine to multiply. No issue. Partial square u over partial x square plus sine t. I didn't see anything wrong here. But this one, oh, there is something wrong. The dependent variable u is multiplied by its partial derivative. This sort of nonlinearity. This equation, the third equation, partial square u over partial, this is fine. Y, which is the independent variable, is multiplied by the dependent partial derivative of the dependent variable, which is fine. This is linear. Non-linear, this one, let me see. X partial u over partial x, it's fine, no issue with this. Y partial u over partial, also it's fine, because u is function of x and y. X and y multiplied by its the derivative of the original function, it's fine, no issue. But u square here is sort of non-linearity, because u is the dependent. The issue is with the dependent variable itself. Non-linear. This equation, the next equation, you see here in brackets, partial over partial s rises to power 2. This is sort of non-linearity. Okay, sine u, sort of non-linearity. And this is, I think, here is no issue. You can see here it's multiplied by 2, no issue. This is normal, equal to sine x. X is independent variable, so again there is no issue. So until now we understand what the meaning of partial differential equation. Its function related to more than one variable, dependent variable, independent variable. Okay, we can solve it by, later on we'll see that solving it, getting the original function, or if we want to differentiate, then we will differentiate with respect to specific variable. We need to specify this at the beginning. We define the linearity and non-linearity, homogeneous and non-homogeneous. Order is the same discussed previously in ordinary differential equations. This is the how it look like the homogeneous. You see equal to 0. This is the partial differential equation equal to 0. Here homogeneous also partial differential equation equal to u, because u can be transferred to the left hand side, will be minus u, again it is equal to 0. But here this is non-homogeneous, because the function here partial differential equal to f of xy, function of the dependent independent variable. So this is the non-homogeneous, similar to what we discussed in ordinary differential equations and in Laplace. Now, you need to understand behind why we study this, why we study partial differential equation. Behind this is we have some systems, the function itself is related to more than one variable. Okay, I will give example of my research. I'm doing research in solar energy. I have solar cell, solar panel, and the solar panel production related to different parameters, such as solar radiation, ambient temperature, wind speed, and many other parameters, humidity. So when I want to check how it behave, how it perform, how it look like the characteristics, what is the productivity, what is the efficiency, what is the power, what is the energy, I need to look in terms of which variable I'm looking for. Is it the solar radiation? Is it the temperature? You got it? Because many variables are playing here, and this is the reality. Reality is for any system you will work, you will find you have many variables. You need to consider them or specify which to take in consideration. In this situation, you keep other variables as a constant. You need to have this assumption at the beginning. These are sample of many well-known equations, second order partial differential equation in different specialty, in wave, this is called wave equation, heat equation, Laplace equation, and so on. You can see here, by the way, these known formula or known equations, it's like, you remember when we discussed in level 1 straight line equation, y equal cm plus, sorry, mx plus c. It's well-known formula for any straight line. When we discuss the quadratic equation, ax squared plus bx plus c, it's well-known formula, and we say that these functions, these formula, representing many systems available in our world. Okay, the same thing here. Partial differential equations, there are well-known formula applied in different specialty. Scientists gave them names such as wave equation in 1 dimension, in 2 dimension, heat equation. As you can see them, we will solve some problems later on some of these equations. Now, how we solve them? How we solve them? As I mentioned, we will, if the function y, sorry, u, given to you with different variables, that's x and y, you will easily differentiate them, considering with respect to which one of the variables you are going to differentiate. Is it with respect to x, with respect to y? Okay. Now, integrating to get the solution, this is something else. And when we compare with ordinary differential equations, if you remember, we integrate, we solve to find y. We are given y dash, we solve to find y. And y, when we solve it, when we integrate, we will have constant. You remember what we call it? We call it integration arbitrary constant, c. How we find c? At that time, initial condition given to you to find c. Without giving you initial condition, you cannot find c. You will have infinite number of solutions, many solutions. The same thing could be said here. I mean, your function could be solved, but you come up with different values based on the constant, or if you have variables based on the variables, such as if you see here, u equal x squared minus y squared. This equation have many solutions, because whatever you assume here and here, you will find u. Without having initial condition, you cannot find the solution. You need boundary condition, initial condition to solve it, as I will explain later on. Still, with the introduction, I will try to finish here the introduction and then start with some problems. You will understand the idea easily here. Now, representing solution for partial differential equation. In ordinary differential equation, we have x and y, we sketch them, very easy. And if there are many curves, we are given initial condition, we can find the final curve out of many. Now, for partial differential equations, we can represent them here using three main ways. The first way is curve where we have x, we have on the y-axis here is the, or we learn to use x and y. Here, the vertical line represent the function, which is u. The horizontal line represent the which one of the function we are dealing with, which one of the variable. Is it x? Is it y? Is it t? So you see here many curves with different colors, different the function in respect with to related to different variables. I mean, each one of these curves are related to one variable. Is it x? Is it y? Is it t? Sometime, as example here, a 3-dimension. We use a 3-dimension. Let's assume my function is capital T, which is function of x1 and x and t. Okay. On the vertical is the original function, the dependent variable. On the horizontal, we have here this line, and this line represent the independent variables. It's vertical on them. Sometimes we represent the function, okay? By the way, in this level, we don't need to plot, we don't need to use them, but you need to know how it look like. Maybe in higher levels, you will use them, but at this level, we don't need them. But we need to know something about them. Now, here, sometimes we represent it by network. You see here? This network, you see some vertical blue lines and some red lines. This is like a network to represent which variable we are talking about. Okay? It gives you the function at specific variable. As example, at this point here, t 5.2, blue line represent at this point the variable x, let me say, and the red line represent the variable which is t. Now, how we differentiate partially? Let me start with simple examples. Have a look. You remember this cylinder? Okay, you study this in foundation and you solve problems. Even you integrate in level 1 in first semester an integration topic to find the volume. Okay. Now, the volume for the cylinder is very simple formula, which is pi V equal volume equal pi r square h. Now, we have pi, which is constant, r is the radius, and s is the height, right? So the volume of this cylinder depend on two variables, r and h. So we have two independent variable, r and h. When I see this simple, I understand directly it is partial differential equation. Partial differential equation of V with respect to H. It means I will differentiate the formula here, keeping R as a constant, only differentiating H. So if R is a constant, it means pi R square, we keep them constant. We don't touch them. We go to H. If I want to differentiate H with respect to H, it gives me 1. Very simple. This is clear, this point? Is it clear?
Yes, doctor.
Great. Now let's go for the same formula, but I will differentiate with respect to R. You see R here? Okay. Now this means pi is a constant. I will treat H as a constant also. I don't touch it. So pi and H are constant. I just come to differentiate R. R squared become 2R. Very simple. Is this clear, easy?
Yes, doctor.
Great. Now also, if we have the surface area of the same cylinder, which is equal to 2 pi RH. Again, if I want to differentiate with respect to R, I keep 2 pi H constant. I differentiate R, it will become 1. If I want to differentiate with respect to H, as you can see here, I keep 2 pi R as a constant. So differentiation of H is 1. So this is what I come up with. More examples. Let's consider, okay, second. Let's consider this equation here. Z equal x square y to the power 3. And he asked me here to differentiate partially, you see partially, with respect to x and then with respect to y. Now when I come to with respect to x, y to the power 3, I keep it. I don't touch it. Okay? We don't touch y to the power 3. We treat it as a constant. I only differentiate x square. Its differentiation is 2x. That's it, done. Now let's repeat the same partial differential equation, but with respect to y. When we talk about y, we keep x as a constant. You see here, x square, I keep it. I don't touch it. Now I go for y to the power 3, differentiated is 3y square. Now I approach here. This example, is it clear?
Yes, doctor.
Now, what if he gave me function u in different items, x square plus xy plus y square? It's very easy. We differentiate each one separately. Now, see here, partial u over partial x. He told me that differentiate this function with respect to x partially. Let's see, this is x square, its differentiation is 2x. This is xy, its differentiation is y, because y is a constant, differentiation of x is 1. This is y square, there is no x here. So differentiation of y square is 0. So at the end, I got this result. What if he told me that differentiate with respect to y? Again, let me back here. This is x square. X square, differentiation of x square with respect to y. How much I come up with? What do you think?
X square. 0, 0.
Okay. 0, excellent. No, 0, 1, 0, Sarah. Okay. Okay, xy. When I differentiate
Y.
with respect to y, with respect to y, not x. Excellent. Okay, y square, differentiate with respect to y.
Y.
Excellent. Now next, I go for another example here. You see, I'm changing the variables, but the idea is the same. Here, z equal x to the power 3, y to the power 3 minus 2 x square y. He told me differentiate with respect to x. I will say, okay, this is 3x, this is 0, this is minus 2 by 2 minus 4xy. Very simple. Are you copying? Are you following?
Yes, doctor.
Great. Now let's differentiate with respect to y. This is x to the power 3, its differentiator will be 0. This is 3, y to the power 3, it will be 3y squared. This is minus 2x squared, y, it will be 1, right? So I approach here. For the next one here, you see z, next example, z equal 2x minus y in a bracket, x plus 3y in another bracket. Okay, two functions, like two parts, contain two variables, x and y. How we solve them? Let me take you back to the principles when you have y equal u v, and we want to find y dash. Okay, what we did, we say, okay, u v dash, sorry, okay, plus v u dash. You remember this when we have multiplication of two functions?
Yes, doctor.
Great.
Yes.
The same thing could be applied here. Have a look. Okay, now here I will say this 2x minus y is u, and this x plus 3y is v. So I will say u, keep it, differentiation of this part with respect to x, it will be 1, this is 0, so 1 plus 0, plus, then v, I keep it here, u dash, it means differentiation of this part, 2x minus y, its differentiation will be 2 minus 0. Very simple. And then simplify. This part, is it clear?
Yes, doctor.
Yes, doctor.
Great. Now let repeat the same discussion, but when differentiating with respect to y. The same thing. This part, the first bracket here is u. This 2x minus y is u. And this one, x plus 3y, is v. So u differentiation of this with respect to y is 3. Then v differentiation of this part with respect to y is minus 1. Then simplify. This one is fraction, contain x and y. He wants me to differentiate partially. Let me also remind you with the principles. Okay. Okay. Let me come here. If I have, let me say y equal u over v, two function. Then y dash will produce v u dash. Okay, minus u
UV dash.
excellent over
V square.
excellent over v square. You remember this formula? Great. We just need to substitute. Very simple. Have a look. This is v. I will put it here. U dash, differentiate this part with respect to x, it will be 2. Minus u, I will keep it. V dash, it means x here, it will be 1. This one 0, okay. Over v dash, this part will be square. Clear?
Yes, doctor.
The remaining is just merit of math. Okay, simplify, you find the answer. Okay, let me see if I repeat the same thing, but partial derivative with respect to y. Now, here, also v, I take it here. Differentiate this part with respect to y is minus 1. Then this part, keep it here. Differentiation of x plus y will give me 1 over the square. And the remaining is merit of solution. Now, if this is clear, can you solve the next one here? Z is given to you 5x plus y over x minus 2y. Yeah. Solve it partial differential this part with respect to x only. Can you do it and tell me what is the solution? You got it?
Minus 11y over x minus 2y square.
Excellent, excellent, excellent. Anybody got it also?
Yes, same.
Excellent. So I don't think we need to spend much here. Let's go for the next point before I give you some exercise to solve. Okay. Let me see. Okay, I have one more point to finish. Okay, so let's solve more problems. Can you solve this one here? Partial derivative of only with respect to x. The first one.
Okay, doctor.
Solve it and tell me. With respect to x,
plus 3y.
sorry, repeat again, Sarah.
8x plus 3y.
Excellent, excellent. Whom found it else? Same. Okay.
Same. Yes.
Now,
3.
okay, thank you. What about second one? What do you think? What is the how we will solve it with respect to x? We use the formula of y equal
Yes.
uv, right?
Yes.
So do it, please. Do it and tell me what is the solution with respect to x only. How much you got it?
Wait, doctor.
Okay, okay, okay. I learned to say, did you finish?
Three x plus 2y.
Okay, 3x plus 2y. You multiply 3 by the brackets and then 4 by the bracket, right? Whom found it else?
It's equal minus 7y, doctor.
Okay. Whom found it else? Minus 7y?
Yes.
Let me just a minute solve it by myself. Check.
No, doctor. 24x minus 7y.
Oh, okay, sir. Just 1 second. Okay. Let's see. Z dash with respect to x. Oh, let me say sorry. Z small x here. It means we differentiate partially with respect to x. It will be 3 multiplied by the bracket, which is 4 x minus 5 y, okay, plus 4 multiplied by the bracket, 3 x plus 2 y. Can you tell me what is the solution? What is the after you simplify what you come up with? Sarah, do you?
24x minus 7y.
Okay, whom found it out?
Minus 7y.
Excellent, excellent, excellent. Kauthar, right? Is this Kauthar?
Yes, doctor.
Okay, okay. I recognize your sound. Okay, voice. Let me just give you a hint about these two next questions, 3 and 4. For 3, what do you think? What is the idea? It is tan. What we should do? You have an idea, or I give you the idea? Tan.
doctor, tan 3x plus tan 4y.
No, just a minute. Tan is sine over cosine, right?
Cosine.
Yes.
So you have a fraction. It means like u
Yeah.
over v, right? You do it like this.
Yes.
Easy?
Okay.
Okay, the second one is clear. It's a fraction, also u over v. So you can't do it later on when you have time. Try to do it. Okay, practice on this. It's easy. Okay. Now here more examples. I think we need to go to the next point I would like to cover to close this session. Now, sometime the function is not clear in front of you, not given to be. As example, this one here. V is f of x square plus y square. He told you that there is function v, which is the dependent variable. It is of x square plus y square, but what we don't know what it contains. And he wants you to show that x multiply x, just a minute, x multiplied by partial v over partial y minus y multiplied by partial v over partial x equal to 0. So we don't know what is inside the function. We just know it's function of x squared plus y squared. Okay. This remind me with what you study in level 1 in semester 1, function of function. It means y, okay, when you want to find dy over dx, where x also is function, so contain variables. So what you did, you define it to be dy over du, the intermediate function du, okay, dot du over dx, because it's the same. I mean, if I cancel this part with this part, we back to dy over dx. So it's called function differentiation of function of function. Inside function, there is another function. It's y, inside y, not x. Inside y, there is another function, which is g of x. You remember this? You studied this in level 1. You remember 200 years back? Last
Yes,
year.
doctor.
Okay, last year we
Yes,
studied
doctor.
this. The same thing could be say here. You see how we will work on this. We will say, okay, partial v over partial x, okay, this is sorry, okay, this is u, okay, so dv over du is given to you, f dash of x squared plus y squared, plus, now you differentiate the variable u. This is u with respect to x. It's easy to differentiate this. It will be 2x, right? The same thing here. Partial v over partial y. It is f dash of u, which means dv over du. Here is du over dy. This is u, which is x squared plus y squared. You understand what I'm talking about, or it's not clear? You want me to explain it on the paint? Is it clear?
Not clear. No,
Not
doctor.
clear. Okay. Not clear. Not clear. Okay. Have a look. Have a look. Just let me. Great. Okay. Now we say that. Let me write it again. Dy over dx. Let me say. I just to remind you the function of function. You studied this before in level 1, semester 1. Is dy. Okay, over du. This is the function of function. Function inside u, inside y. U is function inside y. Du over dx. Okay. Let me do the same thing principle on the same part. He asked me now, I will make a line here. Partial v over partial x. Okay. I will say, okay, this mean, okay, partial v over partial u dot partial u over partial x. Agree? Is it clear?
Yes, doctor. Yes.
Okay. Partial v over partial u is f dash of u, which is x squared plus y squared. Now, if I want to differentiate u, which is x squared y squared here, I differentiate with respect to x only, which became 2x. The same thing could be say for y. The same thing. Also the same function, but here we differentiate with respect to y, it becomes 2y. Now, if I talk this part and I talk these parts, so substitute for partial v over partial x, partial v over partial y here, this one and this one. So you see x by the result here, which is this one. Here, this part. Minus y by the result, this one, this result. You see, minus y by this result. Okay. Now let's simplify. Just a minute. Let's see. This is x multiplied by 2y. This is y multiplied. It is the same. F dash of x square, y square, f dash of. So it's the same. It's the same thing minus itself. It gives 0. Oh, we prove it. Left hand side equal right hand side. Clear?
Yes, Doctor,
Hello?
clear.
Yes, doctor.
Great, great, great. Now, more problems here, okay? What I want you to do to solve A. Can you solve A? I think it is with respect to x, partial derivative with respect to x. Just tell me the solution without writing on the paper. Just have a look at it and tell me.
6x plus 2y.
Excellent. That's it done. If it is with respect to y,
It's equal 8. 2x plus 8y.
z equal sign is sine x, y. If I ask you to differentiate with respect to x, what you will find? What do you think?
Minus cosine y. Minus cosine y.
Look. Just a minute. Let me remind you with differentiation of sine. If you have sine a x, this is y. Okay. Then
Equal
y dash.
a cosine ax.
Excellent. A cosine ax. Excellent. Now a here is the constant of the variable, the independent variable, right? Now I ask you here to differentiate with respect to x. So how we treat y as a constant, right?
Y cosine xy.
Excellent. Now the next one here, I don't think please, whatever we don't solve here, try to practice at home. So it's easy because it's fraction. So it means v u dash minus u v dash over v square. Okay. And then he told me, I want you to solve these two problems after we finish this session. Practice on them. But let me explain before you go further. He told you z equaling exponential x plus y exponential y. Prove that partial z over partial x plus partial z over partial y equal 1. So what you will do, you will differentiate this with respect to x and then with respect to y and add them. If you got 1, then this means left hand side equal right hand side. The same thing for this function. This function, you will find its function of function similar to the previous example here. Please try to follow the steps here and apply them in this example. I keep these as exercises for you to enjoy today and solving them. I will stop here. Do you have any question?
No, Doctor.